Guys, Buildzoid here, and today we're going to be taking a look at the GTX 2080 FTW3 PCB from EVGA. So this is one of the first custom GTX 2080 PCBs that we're going to get to, well, actually one of the first GTX 2080 PCBs to look at, period. It's very impressive. But that seems to be the case for like the entire 20 series lineup. Even like the reference cards are getting kind of ridiculous. And I wonder if it's maybe just because they're expensive and not so much because they actually need it. Because judging by the Titan V, these things still don't scale with voltage. So there's not really any reason to ram a ton of power into one of these cores unless you're on liquid nitrogen. And this card right here is already excluded from liquid nitrogen use by virtue of this memory power circuit being where it is.
Before that, this video is brought to you by us and the Gamers Nexus store at store.gamersnexus.net. You can pick up one of our mod mats now on back order because they keep selling out, or you can grab one of our other products like the Raglan two-tone hoodie, which we have in stock, or the full Gamers Nexus logo t-shirt that we just restocked in cotton and tri-blend. Learn more at store.gamersnexus.net.
Nice PCB. It's just I wouldn't like you can't use it on liquid nitrogen just because that's where that's right there. And that's going to get in the way of any liquid nitrogen pot you're going to try to attach to this. And that's kind of a major problem in my opinion. So that's your VMEM VRM up there. The card also comes with a BIOS switch. V-core is of course this giant strip right here. Which that VRM is so big that they've actually ended up making the PCB a lot taller, which I think they kind of have a lot of empty space here. So honestly, they could have gone for one of the more like oddball VRM layouts where, you know, that they like put like half the VRM here and then the other half of the VRM here, and then they could have probably crammed the memory VRM up there somewhere. Though there are downsides to doing that because essentially you have one half of the VRM doing less work than the other half just by virtue of being further away from the GPU core, as well as having some extra power loss across the power plane just because of the distance. So, you know, this is better in terms of power delivery. It's just worse in terms of making the card bigger without, you know, really maximizing the usage of the PCB space. Then again, most of these cards are apparently loose, like very closely based on the reference PCB, which kind of makes sense because this looks like they just took the reference PCB and added 4 more phases to it and then moved the memory circuit. So, as well as switched, added and put it on dual 8 pins. So you have that there. For power monitoring, standard NVIDIA, you know, you have a Texas Instruments INA3221 down here. And, that also means that you can do all of your typical shunt mods with liquid metal, stacked shunts soldered on top of shunts, long piece of wire soldered on top of shunts, which with the long piece of wire soldered on top of shunts, you need to actually be kind of careful with how long that wire is. If it's too short, it's going to trip safety on the card where it'll think that there's a malfunction because the power reading is too low, which is also the reason you can't just directly short over the shunts. If you don't want to mess around with modifying the actual shunts, there's a bunch of capacitors around the INA3221, which are used for input, for filtering the actual voltage drop across the shunts before it gets into the sense pins of the INA3221. And if you want, you can apply a resistor across those capacitors, typically around the size of 10 ohms. And that'll give you a, say, 3 times increase in power consumption. It really depends on how that filtering circuit is actually wired up, though. But on some of the 10 series cards, if I remember correctly, a 10 ohm resistor would give you a 3 times increase in maximum power consumption. And like, it would allow the card to pull 3 times more power. Not that the card would actually go and do that, because obviously it's not going to pull power it can't use. So, you know, standard NVIDIA right here with the current monitoring setup, and that's kind of normal. And then you have a bunch of minor VRMs over here, so you're going to have things like the 1.8 volts VPP rail for the GDDR6. I'm so used to saying GDDR5X for high-end NVIDIA at this point. But GDDR6, which isn't that different from GDDR5X actually. Like in terms of power requirements, it's very, very similar. It runs on 1.35 volts on the VMEM rail, or VDDQ if you want the technical term that the datasheets use. 1.8 volts VPP. then there's going to be, I assume this is going to be PAX. Actually 1.8 volts might be over here. And then, because the thing is, this has a USB Type-C connector, and that USB Type-C connector needs a 5 volts rail, and you can't get 5 volts off of this, because this is 12 volts and 3.3 only. Yeah, that's just something worth considering, that there's going to be a 5 volt regulator somewhere on the card. And this might be 1.8 volts, or that could be PEX. That's also another option, that could be the PEX rail, which sits at 1 volt. But all of these are basically minor rails, and you don't need to worry about them unless they don't work. And if you have one of these cards, you basically, like, they either put out 0 volts, or they put out whatever voltage they're supposed to be putting out, or your chip is dead. So, you know, that kind of thing. You don't need to worry about them that much. If you're on liquid nitrogen, it can sometimes help to change the voltage on the PEX rail. But even that is just, like, not necessary, like, not always necessary. So that kind of covers all the different VRMs we have on here. Now let's get into the major sort of into the details of them. And this is where the big upgrades start with the 20 series. So with the 20 series, NVIDIA has apparently gotten UPI Semiconductor to make a new voltage controller. Say hello to the UP9512. It is a whole +1 over the UP9511, which you had on the entire 10 series. So UP9511 was the predecessor, that was on the 10 series. And there's actually a massive difference between these two chips, even though the number's only gone up by 1. Like, I'm honestly surprised that they've not made this a whole new, like, lineup, like a 9611. But no, it's 9512, and the changes are huge. So the 9511, he had a maximum switching frequency of 600 kilohertz per phase. The 9512 goes up to 2 megahertz per phase. This means if you're running a doubling scheme, you can actually still cram 1 megahertz per phase, which is more than enough to max out any power stage or really any transistor configuration. So that's a nice upgrade. They still both output, you know, they're still both 8-phase outputs. So configurable up to 8 phases for both of them. But the UP9512 adds the new addition of an SM bus. So, fun fact about the 9511, if you have a 10 series GPU and you check your vCore reading, that vCore reading is not actually vCore at all. It's literally, like, there's physically no way for those cards to monitor the VRM output voltage, because the UP9511 doesn't have a digital circuit to report how much voltage it's outputting at all. So you don't actually know how much voltage a GTX 10 series card is actually running on. You just know what the driver is telling the chip to produce. So you don't know how much load line is on top of that. You don't know anything, really, about the output voltage. With the 9512, the SM bus is not fully detailed yet, but it is supposed to do monitoring functionality. So, like, VRM output current should be possible to monitor. VRM operating temperature should be possible to monitor, assuming the VRM has temperature sensors built in, which certain power stages will have. You can also just use add temperature sensors of your own if you're the PCB manufacturer. It should also support voltage readouts, and may or may not support, well, it's also supposed to make it possible to change configurations of the voltage controller. However, there's no details on what exactly you'll be able to configure. I'm assuming switching frequency will be configurable, load line calibration may be configurable, and some other operating parameters for the VRM may be configurable, but really we need the, I really want UPI to publish the full data sheet for this chip, because it'll be interesting to see what exactly will be available. And I really hope they publish the full data sheet with the actual register map for this, because if they do make the register map public, that would mean you would have access to things like switching frequency through software, essentially. So that would be really, really neat functionality to have on these cards, and that makes me excited about this new chip, because the 9512 is essentially on par in terms of features at this point with things like the International Rectifier 3595, which was basically the voltage controller of choice for cards like the GTX 1080 Ti Kingpin Edition, the Lightning, the Galax Hall of Fame. All of those cards were on a IR 3595A, and at this point, the 9512 basically matches that, could match that on the feature set, and that would be really, really cool. if it actually did, because, well, that would mean your reference PCBs would be just that much better to start with. So that's the 9512, you know, major, like that's the big difference. Like as far as I'm concerned, that's the big difference between the VRMs of a GTX 10 series card and the GTX 20 series, this chip, like that, because it's the brain of the VRM. So of course that's a major difference. The other interesting difference is that apparently these cards are so damn expensive and so profitable to produce that it makes sense to put this lovely new high-end voltage controller literally everywhere, because this chip right here is actually controlling the 2-phase memory VRM, which is just like, you know, yeah, let's smack an 8-phase voltage controller on a 2-phase. There's another UP9512 on this card for the V-Core VRM because it's actually single output. Like it goes up to 8 phases, but it's single output. There's some other chips where you can go like 8 phases and they'll support things like 6+2, 5+3, 4+4, 7+1. But the 9512 is single output. So it's, you know, anything from 1 to 8 phases, but only one output. So if you're not using half of the phases, well, they're just kind of don't get used to do anything. The other 9512 is roughly in this area of the PCB. I unfortunately do not have a full board, like full PCB shot of the back of the card. And that one's for controlling the V-Core VRM. So somewhere in that area, we have another one. And that one is running in 6-phase mode. And this VRM, as much as it wants to look like a 12-phase, is not a 12-phase. There's certainly 12 sets of inductors and 12 sets of power stages, but there's no doublers on this. And the 9512 can't control 12 phases, it only goes up to 8. So what you essentially have is that you have groups of 2 power stages and 2 inductors at the same time that are basically synchronized. And since they're not out of phase with each other, it's not fair to call them separate phases, right? Because the whole point of phases is that it's the state of a signal relative to another signal. And if you have two phases, like if you have 2-phase power, that means you have 2 offset power signals, basically. Well, power outputs that are offset from each other by, you know, phase separation. And you don't have that here for 12 phases. You only have 6. So this is basically a ginormous 6-phase. When I say ginormous, I mean ginormous, because same as the Titan V, I keep forgetting that that thing is not a GTX Titan, but the Titan V uses a very nice 70 amp power stage from Fairchild Semiconductor called the FTW3 The 20 series cards, at least the reference PCB for the GTX 2080 and the reference PCB for the GTX 2080 Ti, as well as this PCB here for the FTW3 card, all use this power stage. And there's 12 of them in parallel. So this is ridiculous overkill. This is really powerful as far as GPU VRMs go. Honestly, this is not this is comparable to some of the top of the line cards on the top of the line GTX 1080 Ti's. Now, I do wonder if this is actually necessary, because as far as I know, 12 nanometer TSMC still doesn't scale with voltage. So if you're on air cooling or water cooling, you're never actually going to get anywhere near using the capability of this VRM. But, you know, there's nothing wrong with having way more VRM than you're ever going to use. At least if half of the phases failed, you'd still have more VRM than you need. Redundancy. Yeah. Which actually, I do think the FDMF3170s, these are like smart power stages. If I remember correctly, these actually do support like dropping, like if they malfunction, they're just going to drop out and the VRM can keep running like nothing happened. So that's, you know, that's kind of neat. You basically have a nice redundant 6-phase VRM as an end result. Now then, in terms of actual heat output figures for this VRM, it gets a bit complicated because as much as I like the FDMF3170, the datasheets for this thing are spec'd entirely at 1.8 volts out, 500 kilohertz switching frequency, which the 500 kilohertz switching frequency is not a problem. The 1.8 volts output is. because that's going to drive up the heat output of each power stage for any given current level. So if you're pushing, you know, say 50 amps at 1.8 volts, it's going to produce more heat than if you're pushing 50 amps at 1.2 volts out. So that means that all of the heat output figures I'm going to give you right now are a bit high, or maybe very high. I don't know, because the data sheet doesn't say how these scale with output voltage. They do scale with input voltage. Like, there is a graph for scaling with input voltage, but it's just like not exactly useful. International, like, there's a lot of other power stages which actually give you details for scaling with with output voltage, and the differences are quite significant most of the time. But it also depends on the internal design of the power stage. You could theoretically make one that doesn't really care how much output voltage you have, or that would actively get worse as you lower the output voltage. If you had a really weak low side MOSFET and a really strong high side, then you'd slowly run into an issue of the, as you lower the output voltage, more and more of the current goes through the low side MOSFET, and if the low side MOSFET sucks, well, then your your heat output is going to go up and up and up as you lower the output voltage. So, you know, the VRM, basically the VRM heat output figures here are going to be off by some amount in some direction. I'm not sure. Probably upwards. I think they're probably a bit too high. But unless, you know, I get a better data sheet detailing how these actually scale with output voltage, I can't really do anything about this. So let's go through the various current figures. So I don't know how much these cards are actually going to pull, so we're just going to go in increments of 100, starting at 200 amps, because that seems like a like reasonably close to where this probably runs, and I'm assuming these probably run on around 180 amps at 1 volt, but I'm not sure. So 200 amps output, you're going to be looking at about 21 watts of heat output. 300 amps output, you're going to be looking at about 35 watts of heat output. 400 amps output, you're going to be looking at about 50 watts of heat output. Now this, like, all of this is still very coolable, and especially if you were at a lower output voltage and the heat outputs got down, like, this VRM should have no problem handling 400 amps if you just throw enough airflow at it and a reasonably sized heatsink. So I really wonder what's going to happen with the 2080 Ti VRMs for, like, the extreme overclocking cards, like the Galax Hall of Fame or the Kingpin Edition. I'd really love to know what they're going to do if this is what they're putting on an FTW3 2080. Because that's the main thing. Like, this chip is much, much smaller than the 2080 Ti one. So, you know, one would assume that the 2080 Ti is going to pull more, like, a lot more power than a 2080 once you know, take the chains off, so to speak. 500 amps output. This is where the heat output starts getting, like, pretty significant. But again, keep in mind 1.8 volts out. So it would probably be lower if the output voltage wasn't so high. 500 amps output, you'd be looking at about 72 watts of heat, and at 600 amps output, you'd be looking at a little over 100 watts at 102 watts of heat. So realistically, anything up to 400 amps should be perfectly doable for this VRM, assuming, you know, you still have enough cooling. If you don't have enough cooling, you're probably going to be limited to around the 200 amp range. But, like, don't have any active airflow, you're probably going to end up around the 200 amp range. But otherwise, up to 400 should be totally doable. I really do want to know what they're going to do for the 2080 Ti's, like, because this is ridiculous. So yeah, really, really impressive 6-phase. But at this point, like, after the Titan V, I'm not sure that I'm surprised anymore, because the Titan V had basically, like, the same power stages, massive 8-phase where there was 2 power stages per phase, 2 inductors per phase. So it just kind of looks like NVIDIA has just decided, you know what, everybody gets 70 amp power stages and they can just build whatever they want out of them. Package deal. You buy a TU die and you get yourself a bunch of 70 amp power stages to use with it. And so yeah, it'll be interesting to see what the other manufacturers come up with, because this is really, really impressive. And massive, massive overkill. Now then, for the memory VRM, they're still using those 70 amp power stages, which just is, like, it's insane. It's a memory VRM. This thing's never going to push more than like 20 amps, if it's even going to push 20 amps, because GDDR6 is supposed to pull less power than GDDR5. So a little bit less power, or I think maybe the same amount of power as GDDR5X, for the same amount of, bandwidth. So, and maybe even at higher bandwidths. So otherwise the efficiency wouldn't really go up, would it? If it pulled more power at higher frequencies. So yeah, and even GDDR5, which is more power hungry than GDDR6 or GDDR5X, really doesn't pull that much current either. So this is ridiculously insane overkill, and that straight up doesn't need a heatsink. At 20 amps output, that VRM would generate about 2 watts of heat. And I don't think it would actually ever have to push 20 amps, and that's again assuming 1.8 volts. So at 1.35 volts, that would very likely be well under 2 watts, and this thing is huge. If you just have some moderate airflow over it, it should have no problem cooling itself. And if you went all the way up to 40 amps, which I really don't think GDDR6 is ever going to pull, even if you started overvolting it and overclocking it to the moon, it'll produce about 4 watts of heat, which is still nothing for such a, it's a two-phase. It's huge. It has a lot of surface area on the basis of just being 2 phases. So basically, this is this is really, really impressive. That's all there really is to say about this PCB. Is this is really, really impressive. It's just so unfortunate that they stuck that memory VRM right where they did, because there's no way you're ever going to run this on liquid nitrogen, because you need to move those inductors. I assume they do not clear LN2 pots, because they're probably too damn tall. But yeah, that makes it like this thing makes me pretty excited to see the rest of the 2080 PCBs, because if this is what, EVGA has managed to come up with for the FTW3, I mean, maybe all the other manufacturers decide to just like cut costs because it's like, oh, you don't need this. You're just going to get a 6-phase, or maybe they'll just all roll with reference PCBs for their cards, because the reference PCB, as far as I'm aware, is just a straight up 8-phase, which already with this 70 amp power stage, the like freaking 8-phase is already ridiculous. For your typical air-cooled or even water-cooled overclocking. So yeah, very, very impressive from EVGA here. It'll be interesting, but it's just like, it's ridiculous. Like, it's so impressive, it's ridiculous at this point. Because this honestly puts to shame a lot of extreme overclocking cards from the past, and especially now with the upgrade of the UP9512, of the upgrades to the UP9512, like, you may not need a Kingpin Edition 2080 Ti to break world records at this point. Like, no. You might want, like, the main difference between, like, what I expect to happen is, like, the main difference between a Kingpin Edition 2080 Ti and, like, a Lightning 2080 Ti and a Hall of Fame 2080 Ti is that they have better software, like, they have full software controls for the VRMs, assuming NVIDIA allows those to go public, but there's going to be internal tools for that kind of capability for those cards, whereas other cards won't have that. And that's the only difference I can really think of that's going to occur, because as far as the actual componentry goes, like, this is more than enough. This is plenty. Like, you don't need more. So yeah, I'm really interested to see what the rest of the cards look like at this point, because for the first time in ages, it's like improving over the reference design from NVIDIA. Like, this is still a step up from the reference design, but I think at this point it's really unnecessary. So it'll be just very interesting to see the rest of the cards, in my opinion, because we might see some cards which actually opt to just down cost the VRM to try drive down the price point. Because honestly, I think what's coming out at the price point that the Founders Editions are at, this is massive overkill. Like, you don't need this with all probability. But it might be too early to judge. Who knows? Maybe TSMC's new 12 nanometer process scales to 1.5 volts and the card pulls 800 watts on air cooling. That would be uncoolable. So 500 watts on air cooling. That would be coolable. So, and at that point, this VRM might make a modicum of sense. But otherwise, it's just like, well, even then, 1.5 volts for 500 watts, you'd be looking at like little over 300 amps output, which would still be very, you know, very reasonable in terms of the heat. So, yeah, that's it for the video. I mean, there's nothing left to say. This is insane. Thank you for watching. If you like, share, subscribe, leave a comment, any comments or questions, suggestions down in the comment section below. If you'd like to support Gamers Nexus here, then we have a Patreon. There's also a store, which I think goes store.gamersnexus.net. But either way, you can find links to both of those things down below. In the description or the comment section. And also, if you'd like to check out more extreme overclocking content like this, I have a channel called Actually Hardcore Overclocking where I do a lot of stuff like this. So, yeah, that's it for the video, and goodbye.